does it turn red?
It's because it's the focus detection. Anyway, it's now recording.
Okay, so that's what I'm going to talk about.
Welcome to the third switching day.
English, probably. It's independent of what I given said. Now, this is about chapter 4 of Sutherland. And I offered to treat it because I've been interested in some of the questions which he studies in this chapter in the past. And I hope to learn some more. And catch up and find out if algebra has contributed to this area or not. And it certainly has in the sense of there being a number of rather, for me, impossible to read papers getting results about conditional independence which do seem to be new and not proven before. As far as I know, one of them seems to me to be extraordinarily obvious, so nobody bothered to prove it before because it was so obvious. The others seem to be non-trivial, but sort of unfortunately for me, he's really using the chapter as an excuse to tell you all about a whole load of things, namely prime decomposition and primary decomposition, and quotient ideals, and even binomial, lattice, and toric ideals. So that may make some of your hearts beat faster, but it may just be a sinking feeling. So, and I didn't find his introduction to these topics very good at all, because it went so fast and so rapidly, I did not really get, I got some clues, but not more than some clues, and I read some of the background literature he refers to, and that helped a little bit, but it didn't really help me, and in particular, it didn't really help me to understand his sort of big examples which he gives. So the structure of the chapter is, first of all, he gives definitions and some properties of conditional independence. And actually you know it all already because you've heard from Evgeny what independence of random variables means. And he also talks quite a bit about conditional distributions, distribution of one random variable given another random variable. And he emphasized that you should really think about that as being the family of conditional distributions. So if we talk about, let me say, the law, I mean the probability distribution of, but I'll just say law, that's quite common. When we talk about the law of x given y, where x and y are two random variables, we really mean a collection of probability distributions, one for each possible value of y. So this is a sort of sloppy language for the laws, the probability distributions of x given y equals y for each y, for each little y, each possible value that can be taken by this random variable. So, a conditional this is sort of the definition. A conditional distribution is the law of x given y, but what we really mean is the collection of probability distributions of x given y equals y. So what does x is independent of y given z mean? It really means that the law of x and y, and we can brackets around them to emphasize, think of this as one thing. Okay, it's a random variable with two components. X and y are both functions of x comma y. But x comma y is also a random variable taking values in the product space. So what does this mean? It means the law of x, y given z equals z equals the law of x given z equals z, well, sort of times, the law of x given z equals z times the law of y given z equals z for each z. And times means here construct the product probability measure for each little z. This is a probability distribution. this is another probability distribution, and make the joint probability distribution constructed by letting these two components be independent of one another.
Sorry, Richard,
Yes, and please interrupt me.
Evgeny's thing. So
Yes.
this law, this is the probability measure on like omega. So x has an underlying omega.
Yeah,
this
so-
is the probability measure.
So somewhere far back in the background, probably we're thinking we have in our mind there's some random thing going on, and nature or fortuna, goddess of chance, picks an outcome, little omega in omega, according to some probabilities, and then x of omega and y of omega and z of omega and so on are just functions of the outcome. So random variables are just deterministic functions.
To the reals most of
sorry?
the time, right? To the real numbers.
Yeah, so traditionally random variables are real numbers,
Yeah.
are real functions, sorry, but we get very used to talking about random vectors, by which we just mean a list of random variables, a finite list of random variables, and random things take values in much bigger
Okay.
spaces. Actually, not terribly much bigger spaces, because as Evgeny mentioned, the nice things happen. You could sort of say everything you've learned about real random variables stays being true if you're talking about random things taking values in Polish spaces, complete separable metric spaces. So there comes in some topology.
But your laws are functions.
Yeah, and as you're saying, the law of x, which we often write px, is the probability measure on the what you call it,
Value space?
value space. Yes. So you have the domain and the range, but not the image. I mean, okay, the range space. So yeah. So px. So x is a function from omega to let me call it curly x, some nice space, and on this space there is a sigma algebra also, and px is a measure on this space, defined by px of v is the probability, what we write is the probability that x is in v, which is shorthand for probability of, and this is the p on omega, the set of omegas such that x of omega equals
Is in B.
is in B. So yeah, the law of x given y is a family of probability measures on this curve x. Any more? Yes?
When you say that this probability law factors,
Yeah.
do you mean that this happens with probability 1 on the distribution of
Yeah,
Z?
so one has to be precise about things like that, and it should be true with probability 1. Anyway, when we're talking about conditional distributions, these laws of x given y are not uniquely determined anyway. If there's some values of y which are probably 0, you can change them just how you like in a completely arbitrary way. But I always think of them as being probability distributions. Sullivan likes to say if you condition on something with probability 0, I'll make all probabilities conditional probabilities 0. But I prefer that probabilities always add up to 1 and are non-negative and are real numbers. So I would prefer to say it's not defined, but you can still think of it as being a real number between 0 and 1. And so when you multiply it by 0, you get 0. That's better than saying it's undefined, or the 0 of 0. Yeah, so this probability distribution here is it's a family of probability distributions for each set, and under some mild topological conditions they exist, but they are not unique. And if you get any two families, but if you take any two possible such, they're called disintegrations, they will coincide, except possibly at most for for a set of z's with probability 0. So you could also say you could choose them to make them coincide everywhere. Okay, so this is going to be important.
And sorry, it's a silly question. So X, Y, and Z, they all live on the same omega?
Sorry?
X, Y, and Z, they all live on the same omega? Does
Yeah,
that
so we're
also
always
the
talking
same-
about some random variables which are all living on the same probability space.
But they don't have to have the same target, like the curly
No, they
edge.
can have completely different targets, and some could be discrete, and some could be continuous, and some could have values in some fancy polar space, and some could be just plain real numbers, and some could be just some discrete set of labels, like male, female. Of course, nowadays there are even more. LGBTQI, dot, 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 dot. But, okay. So, yeah, so for the time being, let's just say this should be true for all states with, sorry, except possibly for some little states with probability 0 anyway. So for which it shouldn't matter. And, okay, so basically, if you went to Evgen's lecture, you already know what conditional independence means, because it's just independence within a conditional distribution. And this is a notation for it. Now, so what someone wants to do is to show that the assumption of conditional independence between three random variables, and more conditional independences between more random variables, can be expressed in algebraic terms, so that he can get out an algebra toolbox and say things in particular about, if I assume one conditional independence, do others follow as well? That would be useful information to know. And some of these things you know very well already, because you know some things about ordinary independence. You know that x is independent of y, implies that that's equivalent to y is independent of x. So it must also obviously be the case that for every three random variables, that x is independent of y given z implies y is independent of x given z. And this is called the symmetry axiom. And I'm going to explain to you why these things are called axioms. Because they're not axioms, they're theorems, obviously. And one of them isn't even going to be a theorem which is not true. It's possibly the most interesting. Well, a theorem which is true only under supplementary conditions. And one of the things Sullivan does is figure out what exactly are the supplementary conditions. And so here's another one. This is x. Suppose you have two, or in the moment, 4 random variables. And suppose x is independent of y and z. Then it's easy to check from the definition of independence that x is independent of y. You discard some of the information on the right-hand side, and it doesn't change the fact that what's still left there is independent of this. So this is completely obvious, and it has a fancy name. And I never remember these names because they're so unintuitive. So I have to look at them up every time. This is called the decomposition axiom. Sorry, it's called the decomposition axiom if I make it into a statement about conditional independences. So, and obviously we can't go back this time. So this is known as the decomposition axiom of conditional independence. But it's just a very trivial consequence of definitions. And sort of worries about events which have probability zero or things being measurable or not just don't occur. These no supplementary conditions, whatever, are needed to be able to say these things are true. Well, I guess in order to say, no, I don't think so. Yeah. Okay, so let's not worry at that moment. Okay, so what Sutherland now does in the next part of the first part of chapter 4 is he discusses a further 3 axioms, statements about conditional distributions, implications about conditional distributions, which are the first 2 of which are certainly all true with no conditions needed at all, and very trivial and easy to prove. And the 5th one is does clearly need some supplementary assumptions, and I'll explain a bit later why these 5 are important, because they're not just important for this Sullivan's, but there's a whole load of literature about these axioms, and the 5 of them together are called the graphoid assumptions, and the first 4 are called the semi-graphoid, axioms, semi-graphoid. And the reason they're called that is because there is a connection to graphs. And so I can certainly tell you that connection. Well, after doing that stuff, he then has a second section which Bas is going to have to explain to us. And then after that, in the 3rd section, he has 3 case studies, you could call them. And the first one is called the failure of the intersection axiom, so it's not this, but a 5th one, which I'll show you in a moment, because it's sort of so obvious that it fails, and obvious that it's tricky, that it's not clear. It's interesting to study it in detail, but he does study it in detail. Then he has some 2 cases or examples which are sort of interesting. So what he does at some point, he says, well, let's suppose we define a statistical model by, and a statistical model just means a family of probability distributions, by saying that there are some random variables, we call them x, y, z, etc., and we want to assume that these independencies and conditional independencies hold between them. And I'll tell you in a moment why that's important. But for the moment, just the examples. The first example is failure of intersection axiom. Intersection axiom, as it's called. And I don't see what it's got to do with intersection. And I said that these are not axioms. But I can tell you what it is. X is independent of y given z, and x is independent of z given y implies x is independent of y and z. Well, actually the intersection axiom is the same thing by when you also condition on something 4th called w, which you add here and here and here. So this is what's written here is not really the intersection axiom, but it's what the intersection axiom comes down to. And so it's a nice exercise to come up with a proof of this, for which you will need to make some assumptions, as you will discover if you try to do it carefully. And it's fun to see a counterexample. And I'll give you the most simple counterexample I could think of, and it's so sort of stunning and simple. You can wonder why people haven't bothered calling this an axiom or getting into detail about it. So I want to give you 3 random variables where the first 2 have with a joint probability distribution, such that these 2 things are true, but this third one is not true. So here's my example. Take, so I've got I'm going to have an x and y and z. Take y and z the same random variable. Okay, now I've got 2 random variables, y and z, and they have a joint probability distribution, which gives probability 1 to the event y equals z. No trouble, that could be the case. And let x be any random variable which is not independent of y. Or I could also say x is not independent of z. Now let's check that both of these assumptions are true, but this is not true. Well, you can already see that this is not true because I've said I construct x to be dependent on y. So it just means as long as I can invent some probability distributions which are different from one another, I can use them as conditional distributions of x given different values of y, and then these 2 are dependent. But obviously x is also dependent on z, and x is dependent on y and z. But why is x independent of y? Given z, let's look at x independent of y given z equals z. Given z equals z, y is a constant also. It's with probability 1 identically equal to the number z. So I could just as well, I could have written this. But this is z is a constant. If you go back to the definition of independence, you'll find a constant. You'll find that any random variable is independent of any constant random variable. So the distribution of x given different numbers z doesn't change. And so what is going wrong here is that the set of values, the values which x and y can take are, x and y and z can take are very severely restricted by doing this. The probabilities, all probabilities on the diagonal, and that's what's going wrong. And Sullivan does some fancy algebra to show that in general this can go wrong when the joint probability distribution of y and z, think of the discrete case. So here are probabilities p, y, z, probability y is y and z is z. If you can arrange the values y and z in such a way that the probabilities all lie in blocks on the, it's not the diagonal, but on some disjoint blocks, like this. So there's a partition of y, and there's a partition of z, and positive probabilities are only within these blocks here. So there's a partition of y, and it corresponds to a partition of z. Each element of the y partition corresponds to one of the z partition elements, and vice versa. So, okay. So I'll come back to that. But this is then there are 2 more things he does which seem to me more or less non-trivial, not terribly interesting, but I would like to know how algebra, this kind of algebra, helps you to solve it. So he's going to look at models described by giving a list of conditional independencies. And he considers this is curly C, and it stands for conditional independencies. And this is a model, and it's a model for 3 random variables. maybe we tell you what spaces they take values in, but we want x to be independent of y to be independent of z, and z to be independent of x. So we want each of the, for the three random variables, we want each of the pairs, possible pairs, to exhibit independence. What does this tell you about the joint probability distribution of x, y, z? And he has a complete answer in the case where x, y, and z are discrete. Okay, and then the third. So, and I don't follow what he's doing, and I don't really understand the statements he makes at the end. And the third case, so this is about discrete random variables, and his third case study is about multivariate Gaussian random variables, and what he does, so I think Evgeny briefly talked about that, and I'll come back to this example later. Now we've got M random variables, and they have a joint probability distribution which is Gaussian with a non-singular covariance matrix sigma. And he shows that if used with algebra, I think non-trivial and interesting algebra, if you would want to assume that x1 is independent of x2 given x3, and x2 is independent of x3 given x4, and guess what comes next? When we go like all the way to the end and round. xm minus 1 is independent of xm given x1, and xm independent of x1 given x2, I guess. Or
Yeah.
Yes.
Yeah.
That's a circle.
yes, it's circular. It's a circle. Suppose these random variables are jointly normal, non-singular covariance matrix, and you assume for some whatever reason you want to assume this, then you're forced to actually assume. I'm not quite sure if it's if or only if or not. I don't think so. X1 is in. Actually, you're just assuming x1 is independent of x2. Sorry, not just. You're assuming all this, and you're assuming x1 is independent of x2, and x2 is independent of x3, and so on, and all the way to the end. xm minus 1 is independent of xm, and xm is independent given x1. And that's certainly non-trivial. He does it with algebra, and he uses all his stuff about toric ideals and etc. Okay, so that's just sort of a long introduction. And there's a couple more words I want to say about the introduction. Yeah. So why, just briefly, why is conditional independence a big deal and a big topic? It's certainly plays a very important role in many models used in statistics. And I think in the introduction already you talked about Markov processes, and Markov processes are to do with conditional independence, and there are generalizations of Markov processes which are very important in statistical applications. And what they really have in common is that all these applications are about causality. So statisticians teach their students that you can't use statistics to deduce causality. You can only prove existence of correlation. And then, presumably there is some causal explanation for correlations. There's something going on making these things be dependent of one another. I'm using the word correlation in a very loose sense, or just dependence. But conditional independence is very interesting. It's especially interesting because it's a kind of symptom or signal for causality in a particular direction. You very often meet cases where x and y are dependent. So these two random variables are not dependent, but there exist some random variables which, if you know, then these would become independent. And such random variables, so we have this, but x is independent of y given z, is kind of a symptom of which you might be able to observe that z is the cause of both x and y, and the dependence between x and y is just because they both depend in a natural causal sense of z. So this suggests, or it's a sort of symptom of suggests causality. It suggests that z is somewhere behind, happening first, and then x is somehow created, comes into being, but needs to know x in order to come into being, and similarly for y. And that's why x and y are dependent, because they both depend on something which happened before. Lots of examples of that. And so these things are studied not just by statisticians, but by people interested in causality and by a lot of people in computer science, and nowadays in data science and in artificial intelligence. If you want a computer to learn causal structure from dependencies which are out there in data, one strategy is to let the computer look for conditional independencies and then try to arrange the conditional independencies in a way which makes a meaningful causal story. So it's sort of a very big topic, and there are a lot of computer scientists also therefore interested in sort of axiomatization of conditional independence. Okay, so now let me fill in some more of the details of things. Yeah. Okay, let me.
You can use the whole board, Richard.
I can use it.
Like, it's entirely up to you, but the camera captures as much as you want.
Yes, I will use the whole board. So, okay, so let me follow these notes I've written here, because there's certainly some things here I do want to say, even though some of them are repeats. So, so I'm going to be talking for a while about a number of random variables and just talk about elementary things about independence and about conditional independence. And if our random variables will take values in Polish spaces, then joint probability distributions can be disintegrated into a marginal distribution and families of conditional distributions, and more nice things are true as well. So we can then write, so this is the measure on the outcome space, on the Cartesian product of the outcome spaces of x and y. You can write it as px. I'm going to write star py given x, but the point is this is a family of probability measures on the outcome space of y, indexed by possible values of x. And what I really mean when I write that is something like pxy dx dy. So it's a measure on products of the outcome spaces equals px dx py given x equals x dy. And when I write something like that, what I really mean is for any, say, positive measurable function and writing curly x and curly y for the outcome spaces. So here's some function of x and y, dxy, dx, dy. So this is actually just the expectation of that function of x and y after we've moved the underlying probability measure to the product of the outcome spaces. We moved it to x cross y. This is how we can compute the expectation of any functions of x and y, like x plus y or x squared times y or whatever. And this is equal to an integral over x with respect to the outcome, the marginal distribution of x of a function of x, which is the integral over y of fx y py given x equals x dy. So I may write this, and I may write things like that, but this is what we mean. You can compute expectations of any functions of x and y in this way by an inner integral with over the outcome space of y using the conditional distribution of y given x, and then averaging that with respect to the marginal distribution of x. Okay, but usually we don't check independence or conditional independence usually we don't do it by checking something like this. So let's say for all f greater than or equal to 0, measurable functions. What we do is we do simpler things which are available to us when our probability distributions have got densities. And in particular, that's what I wanted to say here. To say that right now, what I want to say next is that so for x independent of y, there's the definition, if and only if probability x in A and y in B equals probability x in A times probability y in B for all measurable sets A and B, and this is true if and only if Px I wrote here P y given x equals x equals P y almost x almost all means with probability 1, and so as long as we can talk about this, and if the joint distribution of x and y has got a probability density with respect to the products of two measures, and then I'll call the Sullivan uses a little f to stand for a probability density function, but I'll write a little p. So this is a small p. This is the probability density of the two random variables x and y, assuming that the joint distribution has got a probability density with respect to products of two measures, which may be say mu and sigma. This is what we often check in practice, if and only if this is equal to fx times g of y for some functions. F and g, where this is joint probability density with respect to sigma cross nu. Sigma is a measure on the outcome space of x, nu is a measure on the outcome space of y, and this is a product measure. Maybe there's some more technical things which should be said, but what you do, that you can think of two important cases. X and y are real random variables, and this is Lebesgue measure and this is Lebesgue measure on the Borel sets of R2. And the other important example is X and Y each take on only finitely many different values. And sigma and nu are counting measure on those sets of finite values. That's on those finite sets. And this is actually just the probability that x equals x and y equals y. So it's just an array of probabilities.
So f,
Yeah.
so f is a real valued function on curly x, is that right?
Yeah, and
Okay.
these are real measurable functions of x and y, and
They would be
they can be
the,
non-negative also.
they would be the probability densities of your.
They would be proportional to the probability densities.
Oh, because
Yeah.
I can multiply one by 2 and the other by a half.
Yes,
in your-
exactly. Yes. So if you take this as given, then you will find out that because this integrates to 1, both of these must integrate to something finite. I think I'm assuming they're non-negative. And they have to both integrate to something finite, and so I can normalize them to make them integrate to 1, which means multiplying one by one constant and dividing the other by another, by the same positive constant. Yeah. So now this is getting close to, so in the discrete case, that's actually saying that if you make the matrix, so there's just finitely many possible values for x and finitely many possible values for y, and that you're simply saying that this matrix, so here are the possible values of x, and here are the possible values of y, and the whole, these are numbers, non-negative, adding up to 1. You're saying this matrix has got rank 1, because it can be equal, it can be expressed as a, what you call it, a column matrix times a row matrix. And it's a non-negative matrix. It consists of non-negative numbers which add up to 1. So it certainly can't have rank 0. So it's a matrix of rank at least 1. And in independence, it's a matrix of rank 1. And Solomon likes to express that in terms of determinants of minus. All 2 by 2 minus are 0. So that, you're right.
That I can explain next week.
What?
That I can explain next week.
Yes, now you don't have to do it. But yeah, so I want to show you how he connects conditional independence to polynomials, identities of polynomials, and also in the joint normal case. There can be different polynomials in different things, but the same trick is going to work. So all 2 by 2 minus, so independence in a discrete case implies, and I think it's equivalent to all 2 by 2 minus equals 0. So here's So we fix an x and an x prime and a y and a y prime. And a 2 by 2 matrix, and the minor of that is p x y p x prime y prime minus p x y prime p x prime y. And so all of these should be 0. And this doesn't, to make this meaningful for statisticians again, I will write it, I will, suppose I can divide by things I like and not worry about 0 by 0 for the moment. You can, if this is 0 for x prime, y, and y prime, that's the same as saying modulo nuisance with dividing by 0. Pxy, px prime y equals px y prime divided by p x prime y prime, the same. So let's just suppose we can do this division for the moment. Now, pxy, that's the probability x equals x and y equals y, and px prime y is the probability x equals x prime and y equals y. So these are both of these proportional with the same proportionality constant to the probability that x equals x given y equals y, and this is the this is proportional to the probability x equals x prime given y equals y. So this equality is saying probability x equals x. So I'm going back to sort of a school level probability theory. X equals x given y equals y prime divided by probability x equals x prime y equals y prime. So in probability language, these are the odds on x equals x versus x equals x prime, given y equals little y. And these are the odds on x equals x versus x equals x prime, given y equals y prime. And so if these are equal, it's telling us that the conditional distribution of x given y is the same as the conditional distribution of x given y equals y prime for every y and y prime. So it's just to make this, to go back from algebra to probability, it has probabilistic content. So the odds on x equals x versus x equals x prime don't depend on y. Okay, so now I can immediately tell you what is the now we turn this into algebraic geometry. Then we so this is basically about Sutherland's notation. So for x, y, two discrete RVs, and we're essentially fixing the number of different values x can take and the number of different values y can take. The independence model is the model which we get, so it's a set of probability distributions which we get by just assuming x is independent of y. And he writes things like this. We define the independence ideal belonging to the conditional independence, sorry, in this case, independence statement, x is independent of y, is the ideal generated by px prime y prime times px y prime px prime y for x in x y, sorry, x and x prime in x, y and y prime in y. In a moment we're going to get longer things for conditional independences, but they're going to be just the same. So that's an ideal generated by this family of conditional independence statements, which in this case is just one independence statement. Yeah.
Sorry, this curly C, is it the set containing the formal symbols, or is it like the set of all pairs of distribution satisfying this independence?
No, it's the formal symbols, I think.
Okay.
Yes. C is always going to be a set of formal conditional independence statements.
It's something from computer science. It's just a list of
It's just a
things
list
you
of
want.
It's a list
It's
of
a list
strings.
of things like that. Yes.